second talk. So it's going to be delivered by Denis Vorotyntsev. He's a senior data scientist at Oura, the Finnish startup, and he will be talking about explaining machine learning models in 2020. Denis, the stage is yours.
Yeah, thanks. Yeah, now you should be able to see my screen. So yeah, first of all, thank you for coming. I'm really excited to be here and present this material to you. My name is Denis, and today I'd like to share, today I'd like to share some thoughts on how to interpret machine learning models with the modern Python tools. So recently I worked a lot with interpretation machine learning, and I have some experience which I'd like to share. Let's start. Yep. Yeah, so I'm working as senior data scientist at Oura. We are making rings for well-being which are capable for tracking your sleep. And we're using this data in order to improve person's sleep and overall well-being. Our most famous and recent project to which I was involved is early COVID detection based on the data collected from a ring. Before that, I was working at VTT, Research Center of Finland, where I was helping to detect anomalies during steel manufacturing using machine learning. I'd like to start my presentation by asking a question. Why do we actually need explainable machine learning? How it can help data scientists to achieve his or her goals, and how it could help a company? Personally, I ask these questions the following way. So imagine we want to solve some business problem, and when we're solving business problem, our main goal is actually optimize profit or some other metric given a set of constraints. So we have some data, we're creating target that we want to predict, and then we will use this target in our business process. Unfortunately, machine learning models cannot optimize profits as is, so we create this proxy metric. It can be, for example, binary accuracy or log loss or anything else. And to optimizing this proxy metric, we claim that the model, the pipeline, which achieved the highest score on the holdout data set, probably is the best model, and we should use this model in our production settings. And now the interesting part begins. When we're collecting data, our collected data is not actually the real world. It's just a representation of the world. It's words mapping. And by collecting some data, we're inducing selection bias by default. By training our model only on subset data of all available data, we're also inducing other sorts of biases. We may create a bug in our pipelines. Models are also just a mapping of the data, and so on and so forth. So at the end, we may end up in the situation where our final metrics, our final proxy metrics, such as accuracy, might be pretty good on the holdout and test data sets. But in reality, our solutions are suboptimal. So they're optimal for our proxy metrics, but they're not optimal for our metric which we want to maximize, which is profit or any other utility metric that we want to use. And for me, the possible way to solve this problem is to actually start interpreting our models, start to understand what is going on under the hood in this black box of the model. And for me, this interpretation is just a final stage before pushing models to production, is to test our model. Is it actually delivering what we're expected it to deliver, or just overfitted towards some artifacts in our data set or biases in the data set? And this problem of bias is actually really important nowadays. If we go to Google and Google AI biases, we will find a lot of articles related to the topic. And the society, the people are really interested to understand that the models which were created as data scientists are actually not using these biases, that they're not biased in any sense. And also, this topic of interpretation of machine learning models is quite popular in the papers in the scientific world nowadays. So since 2010, we see an exponential growth in the number of papers on the interpretation machine learning, which is pretty nice. But personally, I feel this gap between what researchers can show us, can write about, and the actual data scientists who are creating these models and pushing them into production. And for me, the place of interpretation machine learning is something between evaluation stage of the ML pipeline and deployment stage of the machine learning pipeline. And I talked with a number of data scientists. We discussed how they approach interpreting machine learning models, what decisions they made after interpretation, and so on. And I had this feeling that in reality, interpretation is just not very useful stage of ML pipeline. You just calculate SHAP importance for every feature in your data set. You show, let's say, top 5 most important features to your stakeholders. They replied, well, that looks good to me. Let's push it into production. Or even they don't say that, it's fine. So it's probably model knows best. This idea is actually taken from the paper called Interpretability, in which authors asked data scientists what decision they are making based on the interpretation, and it turned out that no matter what interpretations will be shown to the data scientists, they are willing to push machine learning to production no matter what. So to check if it's really a problem, because obviously it is a problem, but is it actually a real problem, or just I talked with a data scientists who are not very into this field? I decided to ask the following questionnaire in the 2 communities. First one is MLOps community, second one Open Data Science, 2 very famous data science related communities. And the questionnaire was following. So select which describes you or your company best. 3 options. First one, we don't interpret our models or do it occasionally. Second option, interpretation is a part of our pipeline, but we only calculate SHAP importance. And the third one is that interpretation is a part of our data science pipeline, and we use several models such as SHAP, LIME, GAM, PDP, and et cetera, et cetera. And it turned out that just 6% of data scientists in open data science out of above 100 participants, they answered that they actually use something besides SHAP. The vast majority of data scientists are not actually using any tools or just calculating SHAP. So the problem which I described on the previous slide. And I believe it is a problem. Why it is a problem? Because SHAP is a great tool, no doubts here. It's probably state of the art for finding most important features for your model. But it cannot, by design, answer other questions, such as what are the most important training points in your data, or what is dependency between feature and prediction globally according to the model, and all other questions which are listed on the screen. And these questions, they're actually really important, because when you're trying to interpret your model, you try to understand how it's making decision. You cannot only use most important features, because it's not the only question you should ask. You should ask several questions. And that's why I'm actually proposing to use the framework which I'm currently using myself. So it's pretty simple. It's not perfect, obviously, but it's okay for me, at least. It consists of 4 main questions, which I ask during interpretation. And after answering each of those questions, I make a decision, should I rework this model or continue to the next stage of interpretation. Let's go through each question step by step. So the first one is following. Do we have the same metrics across different subgroups? And here subgroups could mean like anything. It could be subgroups based on some cohorts of users, such as gender, race, age. We want our model to perform well enough on all of those groups, because in our production settings we are expecting to see all of those users. Also, subgroups could be some clusters in the data which are not related by user race, for example, or gender, but related to something else, maybe number of purchase or something else. And so the question that we want to answer again is that we want to see the same metrics across different subgroups. If we are not seeing same metrics across different subgroups, it might be a signal that you have a bias in your data, and you try to find those biases and remove it. Or it might be again an artifact of the data set. For example, the subgroups can be different, and that's why model just find these differences between those subgroups, and the final results are because of those differences. In that case, if it's normal, if it's not because a bias in the data set, you may just create different models for those different subgroups. And commonly, the performance of several models trained on different subgroups is better than just one model which fits them all. Personally, I use my own custom script, which just generates a report for predefined set of groups of users, and I just check the scores manually. But I really like this idea, which was presented by guys from Uber, the library called Manifold. The idea is following. So we train our model. We are making predictions for our holdout data set, and then we cluster our data based on the difference between actual prediction and actual label. So on the right part of the screen here, you see upper image. You see three clusters, three segments. The x-axis is log loss, and we see that for segment number 0, the log loss is low, which means that for this subgroup of users, model performs extremely good. For segment 1 and segment 2, log loss is higher, and we may check why model made a mistake in those subgroups. And we may again use Manifold here. We say that segment 0 is group 1, segment 1 and segment 2 is group 0, and we compare different features based on those different clusters. And we may see that, for example, bottom picture, feature number 0 has a different distributions across two different segments. And it might give us insights on what should be changed in our processing, or it might tell us that, hey, maybe it's worth adding a new model and train two separate models for these two separate segments of users. The next part, the next question to ask is, what are the most important features of the model? And here we are checking if the most important features are actually expected. So what I do, before looking into most important features, I just write down list of expected features and then compare it to the features which are achieved by SHAP or any other tool. Why I'm doing that? Because if I'm not doing that, there is a risk, there is a chance of me doing hypothesis after results are known. It's not a good bias, and that's why I'm trying to avoid this, making hypothesis after seeing results. Because again, in some cases, you might just say, hey, well, it's unexpected, but it still looks good to me, so let's move on. And I want to avoid that. So here, this is pretty straightforward. The state of the art is SHAP. I recommend to use it for finding most important features. If you're training tree-based models such as LightGBM, XGBoost, pay attention to the gain importance of your models. Also, you may find very interesting library called Dalex. This library could provide you the pretty pictures. One of them are presented on the bottom part of the slide, right part of the slide. So this library is actually calculating very same output as SHAP, but it is presented in a better way. In SHAP, the output for each local interpretation is just log it. In Dalex, it's converted to probabilities, and I find this plot more beautiful than one in the one is generated in SHAP. And also, I know that some data scientists are using Lime for both global and local interpretation. Sometimes I don't recommend to do that because Lime has a lot of problems, like three but very huge problems. First one is that the fidelity of Lime interpretation is really low. Fidelity is an accuracy of your surrogate model, in our case, in the case of Lime. So the accuracy of surrogate model is not high enough, and that means that interpretation is not also very accurate. And the second problem of Lime is that interpretation are actually based on the choice of hyperparameters. So depending on what hyperparameters you're going to choose in Lime, you may end up in the situation where you have just contradictory interpretations, which is not a desirable property of interpretation tool. And the third problem is that interpretation depends on the input a lot. So if you change input even slightly, you may have a different interpretation. So interpretations are not robust towards small distortions in the input. Many interpretation tools have this problem, but Lime has it like in the worst possible state. Next question to ask. So we determined most important features. Now it's time to find what is the dependency between feature and target and prediction according to the model. And again, we're checking if our dependencies seems okay to us. We're checking if dependency does not have these bumps and beats, because this again is symptoms that you have some problems with your data. And there are several tools to do that. I personally use accumulated local effects in alibi library, but partial dependency plots are good, is a good choice as well. So I recommend to pay attention to those stuff. And also the library called Interpreted. It's just a brilliant idea. I really like this library. I used it quite a while. So this library cannot make your models interpreted. Instead, it is training fully interpreted, fully white box models from scratch. And the idea is following. So in all models in machine learning, we're training model, a function f, which takes all input features and try to create this function which predict the target. In additive models, we are doing quite a different stuff. So we create a separate function for each input feature. And these functions f1, f2, fn, they're called shape functions. And then, of course, we just combine the results of the final predictions, just a combination of all of those shape functions, output of those shape functions. And the huge plus of this approach is that by doing so, of course, we're not taking into account intersections between features, which in some cases is very good for very bad for our problem. But by doing so, we actually could inspect each of those shape functions and understand how this particular value of this feature affect the final prediction, like what is contribution of this feature, which is pretty similar to the SHAP, but this is done in a very good theoretical manner, let's put this way. And this interpreted library is quite accurate. It's fully white box. You may see a benchmark on several data sets compared to XGBoost random forest, and the results pretty good actually, even taking into account that no intersections between features were taken into account. And the most important part here is that we actually could inspect, again, those shape functions. That's why we started using this library. So right part of the screen, we call our explainable boosting classifier, we train it, we ask it to show most important features. And for example, in this task, we may see dependency between output of the shape function and age. I believe in years. So we may see that between 20 and 70 years, the shape function seems quite nice, and we may understand this dependency. But after 70 years, the shape function is not smooth. It's just jumping up and down. For example, here for 80 years, the output of model would be 0. But if you are 79, it would be something like +1. And if you're 82 or 83, it will be plus 0.5. Of course, it's not desirable. We want our shape functions to be smooth, and it is a sign that probably in the training data we don't have enough training points, and we may correct actually this shape function. So we set this part of shape functions of shape function, and for this part we may just plot a straight line. It's not possible out of the box, unfortunately, but I think you got the idea. So by doing so, we actually improving our model even further. We're not only explaining, but even improving our model. So we change this part with a straight line, the part after 70 years, and we may retain our other shape functions, or we may keep the results as is and push model to the production. The last part, but not least, is to check how we should change the input so it would classify as another class. And the general idea here is to understand, so we train our model, we make predictions for the validation data, and generally it's a good idea to check on what examples model made a mistake and what features contributed to that mistake. I talked about it previously. One way to do it is to use manifold, but other ways to do it is to take each point separately, the points with the highest difference between prediction and the target, and to find the closest point to the given one, but with correctly predicted class, and compare feature values of those points. And it might give you some insights of the separation curve of your model and what you may do in order to improve your model. So this idea, again, I'm using my own custom script for that. I'll explain later why. This idea is presented in the Google's What If tool. So this tool basically do what I described right now. And it may also show you some metrics across different subgroups. It may show you partial dependencies plots for different features, which is also good attributions of this dashboard. But the main problem that this Google's What If tool works only with TensorFlow models. Of course, you have random forest gradient boosting in TensorFlow. Well, I believe you should have those, but I prefer to use LightGBM, I prefer to use CatBoost, and it's not possible to do that using this tool. Also, you may use variants of counterfactual instances. And this is actually a smart idea. So the idea of these counterfactual instances is following. So those methods are only applicable for models to which you may calculate gradient. Well, basically, it's neural networks. And when you're training neural network, you have fixed input, you have fixed output, and you are updating weights of your neural network in order to minimize the distance between your prediction and your target. When you are explaining your model, on the other hand, you want to reverse this task. So now the model is fixed, and you want to find such input which maximize or minimize the output. And this is a smart idea, no doubts, because neural network, especially if it's a well-trained neural network, if it's model like Oracle model with 100% accuracy, it might find the instances right after this separation curve. The problem is that it is an iterative process, and even after few iterations of this optimization, your points may end up in the spaces where you have no training points at all. So basically, in the space where points are unprobable in general. So maybe you want to optimize a credit score, and output of your model could be, well, you have to work 50 days a week or something like that, which is just not possible. But from models output, it is possible. The idea of this SEM alibi, it's like last example on the slide, is that you just you say to the model, well, you may actually optimize, you may update your input, but please be in the specified circle around this point. Again, it is a good idea, but it doesn't work. I tested several times on my own tasks, and I just end up in the situation where the output is far away from the initial input of the model. And this whole idea of working with gradients looks very similar to the adversarial examples. So these counterfactual examples are actually adversarial examples, but for explaining and making these adversarial examples for your input for interpretation. Well, I'm not very fan of this stuff. Yeah, so this is all from my side. Thank you for your time. Thank you for your attention. This is a link for a presentation, and I will be happy to answer your questions.
All right. Thank you so much, Denis, for the presentation. It was really interesting. And yeah, we have a couple of questions in the chat. And I guess we will start with a very interesting one. It's a kind of philosophical question. So Ari is asking, how do we know that understanding machinery model in general is possible for humans? What does it even mean?
Well, it's actually a great question. And what I specifically like about all papers related to the interpretability is that very, very good papers start by asking what does it mean to interpret a model to the person. And I don't think it's just a question to which we may find an answer because it's really too complex. And there couldn't be any exact answer. But I don't think you're satisfied with this answer. So personally, I believe that if you may if you may copy the exact steps of the processing as model did, that means you understand how it works. So basically, if I may reconstruct the predictions, that means that I can recreate them. What does it mean? So for example, deep neural network with 100 layers with millions of parameters, I cannot calculate all mathematical formulas. I cannot calculate all output of each layer and so on and so forth in limited amount of time. Theoretically, I can do it, but in reality, I cannot. But if we're using, let's say, logistic regression with 5 input features, I cannot multiply each input feature by its own weight and produce an output. And in this sense, I can understand how this model works. So it's probably my answer to this question.
All right. Okay, so let's move to another question. So Andras is asking, how can we use these techniques for large and high dimensional data?
Good question. When you're working with large data set, generally it's a good idea to take a subset of your data set. For example, you may start by training a small model on a subset of data set, or you may use a subset of data set for explaining your model. How to select the size of this subset? Well, that's pretty straightforward. You need to find the such subset of data set after which output of your interpretation tool does not change. And commonly it might be just 10% of your data. Again, it's task dependent, but it might be really small, workable, the amount of data which fits in RAM memory. If we're talking about working with a lot of features, I think generally it's a good idea to run some sort of feature selection or work only with most important features when you are running interpretation. For example, if your model consists of 10K features, I bet not 10K of them are most important, but only maybe 20, something like that. And you must have a lot of time by working only with those 20 features. But again, it's real task dependent.
All right. Okay. So we have another question from Tommaso. He's asking, he thinks that those interpretability tools are only working for tabular data. and where we have clearly defined input features. So what about interpretability for other settings? For example, in the sequence classification problem.
Yeah, my presentation was mostly about, well, it was fully about tabular data, except last part. But anyways, so there are tools which can work with tabular. There are tools which can work with NLP data, with text, with computer vision, with sound, with videos. But personally, I don't work with those types of input data, and that's why I didn't present them in my presentation. But I recommend just to go through most famous tools for interpretation, such as SHAP. You may check Lime, Alibi, and those tools could provide you approaches how to interpret computer vision, like what are most important parts of the picture, text, like what are the most important part of the sentence, and so on and so forth. So it's possible to interpret this non-tabular tabular input data. And there was second part of the question, wasn't it?
Yes, for example, sequence classification problem. How can we interpret?
Well, it actually depends. It's a hard question. I believe that every input data can be every model, every type of data can be interpreted. If we're talking about sequence data, we probably may use again. It depends on type of the model that you're using. If you are using some sort of gradient boosting machine for classifying your input sequence, or just go point by point, you may use the same tools which I listed here, but I would like to add some constraints. So basically, you cannot change the interpretation like dramatically. So two close points should have same interpretation. If we're talking about sequence classification using deep neural networks, well, there are a lot of works in which authors using attention layers in order to find what part of the input sequence contributed the most towards final prediction, like to which part of the input sequence model paid more attention. So basically, answer here: use attention, use transformer architecture to find those attention maps.
All right. Maybe another question in the same context. So Eva is asking if there is any best tools for explaining NLP predictions.
Again, I'm sorry, I'm not working with NLP a lot. I would recommend still check SHAP. It should work with text, and Alibi. Two libraries, both were mentioned in my presentation.
Yeah, I guess as Mehran Ali is commenting here, he said, as long as it's feature importance based on the feature target dependency, I guess we can apply this kind of tools, right?
Yeah, it is actually probably a good question. Can we apply the same strategies for unsupervised models? For example, if you are doing cluster analysis, can we use the same logic for finding most important features? Well, sometimes it's not useful. For example, in k-means there are no important features, but we may transfer the task of unsupervised learning in supervised approach. So basically, for example, we cluster our data. Why not to feed a model to predict the cluster label? And if the accuracy is high enough, that means that we may inspect the supervised model and find what are the most important features which affected these like different clusters. And also there are a couple libraries which can work with interpretation tools from with unsupervised models. Probably I worked with Isolation Forest, the tool which allow you to find what are the most important features for Isolation Forest. Isolation Forest is a tool for finding anomalies in your data. And probably that's it. Maybe there are a couple other tools. Well, yeah.
All right. Yeah, some people are asking about the slides. Are they available after the event? I guess you have this link here with this QR code. Does it redirect to your GitHub or?
It redirects directly to the presentation. Yeah.
Ah, okay. All right, cool. And for people who are interested in getting the slides for Ogojan presentation, please email him at Ogojan. Well, he mentioned his email in the chat, so feel free to reach out to him for the slides. Okay, let's see if there is any other question. Yeah, we have another one from Vladislav. He's asking, is it possible to automate the interpretation if you are training number of models? In other words, do the explanations require a human to make the decision in hyperparameter optimization or model selection?
Well, there are actually two questions. First one, can we automate model training? And answer is yes. We may use different tools for hyperparameter optimization. Personally, I use Optuna to do hyperparameters because, well, general people cannot work in the high dimensional space of choices for hyperparameters, such as, for example, for light GBM, number of trees, depth of your of tree, and number of lists and stuff like that. Models do it much better. So the answer for the first part of questions, yes, we can automate this, and you should do that if you're not already doing that, because it will improve scores of your model by dramatic margin. If we're talking about interpretation, the things are quite tricky here. Generally in the industry, for example, if we're looking at automated machine learning tools such as H2O, DataRobot, Google AutoML, what else? Yeah, I think 3 is enough. So these guys, they're actually trying to add SHAP importance calculation for the pipeline of making the model. And generally, I don't think it's a good idea. And well, it's a good stuff to have this, but it's not good stuff to pay attention to why I'm thinking this way. For me, model interpretation is not automatable at all, because it is a work in which you should make hypotheses and test them using several tools. And I don't think that this automation of hypothesis making and testing is incapable of current state of AutoML. Yes, of course, you may calculate SHAP importance, but still, it's not answering some of your questions. You may create this partial dependencies plot automatically. Again, this is good stuff. But are you actually understanding why you're using these tools? Like why you're calculating these most important features? Why you're making this partial dependencies plot? Maybe it's not even useful in your task. Maybe you should use another tools. So for me, again, I'm sorry that I'm repeating myself, but for me, interpretation is just making hypotheses about your model and try to check this hypothesis with the tools which are available to you.
All right. Okay, I guess we don't have any other questions, but I guess I have one quick question. So what is your take on the Bayesian deep learning for interpreting deep learning models? Do you have any thoughts on that?
Wow, it's a hard one right at the end of the presentation. To be frank, I'm not very familiar with Bayesian neural networks. A year ago, I took part in the Sberbank AI conference. It's a very famous conference in Russia. And one of the presenters was, I believe his name is Gennady Vetrov. He's extremely famous in scientific circles, extremely famous person who spent a lot of time working with Bayesian neural networks and with neural networks in general. And he presented a comparison of different approaches how we may calculate uncertainty in deep neural networks. And I didn't understand a single word he said in his slide because it was a pure mathematics, but I understood the following. So I understood the final results. So if you want to calculate uncertainty in deep neural networks, the best idea, the best approach you can take, again, might be just my understanding, and I'm completely wrong here. We just like cut this out during post-processing. So the general idea was that if you want to collect uncertainty, you should train a lot of runs of the same architecture with the same data, but with different choice of random seed, and then just average your predictions and calculate, let's say, average and standard deviation that will give you uncertainty estimation. It is not an answer to your question, but I think it will provide you some understanding of what I'm thinking about interpretation using deep neural networks. So it's a hard topic, and I'd like to see some results which could work out of the box, and some people who are already worked with such models, and then apply it in my own work, because I'm not a researcher. Well, I do some research work, but I don't want to spend months of research when I have a lot of projects to be done.
All right. Thank you. Thank you for the answers. Well, I guess we still have one last question from Ali. He is asking, what are your thoughts about simple decision trees or association rules for interpretation?
It is actually a good idea to have a simpler models instead of complex ones, generally speaking. Unfortunately, there are not too many tools which can allow you to do this type of interpretation out of the box. But I really like the following framework, which I will describe now. So the idea here is that in our training data, well, commonly training data is large, right? We have thousands of examples in our training data, but very few of them are actually useful. So a lot of examples in the training data are actually just the same examples, but with slightly different features. And we don't need too much training data in order to fit our algorithm, right? So the idea is that we may find the most important training examples in our training data, and then using a smaller version of our initial training data, train a much simpler model. And this approach, it was tested using the SHAP. So in SHAP approach, you calculate the contribution of each feature in the final prediction. But the same approach could be applicable for training data as well. Just calculate contribution of every training instance towards final loss, and select the instances with the highest contribution, and then you train your model on those smaller training data. And the researchers, again, if you want the link to the paper, just DM me in LinkedIn. The researchers found that when we are using smaller training data, but carefully selected and simpler models, we may have, not better model, but quite compatible models compared to these complex ones. And I believe this approach is quite robust, quite good to have in your data science toolbox. Unfortunately, there are no tools which can allow you to do it out of the box, and you need to write this code yourself. And this is greatest limitations of all.
All right. Thank you so much.